I want to go through a really brief exam review for you. The topics that I'm planning to review and go over involve three basic areas. The first one is going to be just generally internal loads, stress and strain, and material properties. Second topic we're going to go over are topics of axial loads, including statically indeterminate problems, and thermal loading, finally torsion. So this is kind of a brief overview, remind you what the main principles are. With internal loads, here's the idea. You have probably some kind of structure. It could be anything, a beam or a frame. Here, let me draw a quick frame. And let's say that this is pinned on one side and it's fixed on the other. Maybe there's a force right there. Maybe there's another force acting over on the side right there. Our solution approach first is to draw that whole free body diagram. You almost always need it. And the goal of that is to find your reactions, your reaction forces, your reaction moments. So what we're looking at when we do this is right here and right here. From statics, you'll remember maybe with a pinned support, you'll have a force in the X and a force in the Y. At a fixed support, you'll have a force in the X, a force in the Y, and a moment about that point, about the Z-axis through that point. You do need to find those first. That is really a statics problem. Next, we typically need to do a free body diagram of the part in isolation to determine the loads on that part. So for example, let's say we do that whole free body diagram to find the loads here and here, but what I actually eventually want is the internal loads at point E right there. In order to find E on that part, I'm probably also going to need a free body diagram of just this bar right here. If there's A and there's B, what I'm talking about for part 2 here is a free body diagram that looks like this maybe, where we have some forces at A, AX and AY, and we have forces at B, BX, BY, and MB. So in step 1, we would have found these forces at B. There are external reactions. We find them from the whole free body diagram. Then we need the diagram of this part. I left something off of it. It's also going to have a force in that 2-force member in the middle. Let's say that goes from point D to point C. That would be the force in member DC, which I probably also don't know right now. But here's the trick. If you already did your whole free body diagram and found these, now on this diagram, you can find the other 3 by summing forces in the X and Y direction and summing moments about a point. So the free body diagram of the part in isolation is used to solve all of the forces that are acting on that part alone. So that includes the outside forces as well as forces from things that it was pinned to. And now finally, your last step is going to be to cut it open and draw that free body diagram. So that part we're talking about going in now to this at point E and cutting right across through E and drawing a little free body diagram there. You're going to take either everything above point E or everything below point E and keep it on your free body diagram. I like to take whatever side of E is simpler. That little free body diagram will still have AX and AY on it. And now at the cut, for a general problem of a general part that's not a 2-force member or anything special, you will have an internal normal force, a shear force, and an internal bending moment at point E. And I intentionally did a vertical part because we usually do horizontal parts, and I wanted to point out normal force is always perpendicular to the cut. Shear force is always parallel to the cut, and moment is about an axis going through this, basically the centroid of the cross section straight out of the page at us. So once you cut open and draw the free body diagram, you can finally find the internal loads, which in general will be a normal force, a shear force, and a bending moment in 2 dimensions anyway. All right, the only special case really for internal loads are if it is a 2-force member, then your life gets a whole lot easier. Remember what a 2-force member is? It is a part that only has forces applied at 2 locations and nowhere else in the world. As a result, the loading on it has to be either tension, if it's that way, or compression if I drew those arrows the other direction. So in that case, we can go and do our cut right now. And if I cut this open and draw the free body diagram of everything to one side of the cut, you'll notice what you get. Here's my tension force. All you end up with that's non-zero is the normal force. So let me call these guys my tension T. The normal force will just be equal to T. There is no shear force, there is no bending moment in a two-force member. So you can save some time. All right, moving right along to stress and strain. Let me remind you of the definitions. We had normal stress, which was Greek letter sigma is equal to normal over area. And the picture we have for that is, here's my area right here. And the normal force, it is an internal normal force, acts in that direction, perpendicular to the cut or along the length of the axis is another way to think of it. Related to that, we had this thing called normal strain. That's a Greek letter epsilon. It's change in length over original length. It's the same long bar picture, but what matters for strain is the change in length. So if there's our original length, and now due to the deformation, this gets a little bit longer, that would be our little delta length. And these length changes need to be super, super tiny. So I might draw them kind of big on my pictures, but in reality, they're very tiny. Strains are not going to be like 10. They're going to be like 0.0003. Those are our normal stress and strain. That's what they physically mean on a picture. We also have something called shear stress. So shear stress, and the equation I want to write down for you guys is the average shear stress in a pin, and it's calculated as the shear force over the area, the cross-sectional area of the pin. There are two ways that this can be set up. One is if we have two bars that are pinned together, we want to find the shear stress in that pin. This is what we call single shear, and the picture looks like this. You got a force to the right and a force to the left. So your shear force is equal to F. That average shear stress is going to be just the force over area. We could also have a little bit more complicated case that we call double shear. Looks like this, just a little bit more complicated. The pin still goes down through all the parts together. We still have a force F on it, but because there are two of these to the right, we end up with F over 2 and F over 2. This is actually a really common way that things are pinned together. Well, in this case, our shear force is actually equal to F over 2, not F. So our average shear is half. It's F over 2 over area. So just a reminder of single versus double shear. And finally, we have one more strain, shear strain. Shear strain is given by the Greek letter gamma, and it is equal to pi over 2 minus theta. So what gamma is if you imagine having a block of material that was a perfect square and you deform it so that it gets sheared somehow, theta is the new angle. Theta is that angle right there of a part that used to be a right angle. So what gamma is if you take the whole pi over 2 and you subtract theta from it in radians, the shear strain gamma is actually that little piece right there. There is gamma. It is an angle in radians. You got shear stress, shear strain, normal stress, normal strain. And the other thing about stress and strain that we did in that chapter was we calculated the factor of safety. Our book uses FS for factor of safety. And what it is it's the ratio of the stress that would actually cause the part to physically break to the stress that we're ever going to allow our design to see. We can either do it with shear stresses or we can do it with normal stresses. Whatever stress would cause it to fail, divided by the allowable. The stress that goes on top right here, these are going to be your yield stress. This is a table lookup. It is the value that someone has measured for you experimentally in the lab, and they're telling you that is the value of stress that will most likely cause your part to fail. The allowables on the bottom, this is going to be our design guide, right? Because you don't ever want to fail. So you probably don't want to get stresses that are right at the failure or yield stress. You want to be safely below that. So we want this factor of safety to be greater than 1.0. And depending on your field would determine how much greater than 1.0. So if you're given a problem where you're told the yield stress is 50 megapascals and you want a factor of safety of 2, your design stress would be 25 megapascals. That's your design or allowable stress. Next up, we did material properties. That all boils down to a stress strain curve that's measured for our material. Stress strain curve has a linear portion with a slope of E, and yield stress is where we stop being linear and we stop being elastic and we start having strange things happen. So we are never in this class going to go out here. That's why we always want to stay well below the yield stress so that things are nice and linear elastic. So E is that linear slope at the beginning of the stress strain curve, is also called Young's modulus. And since we're on a straight line, we can write stress is equal to that slope times the strain. We give this guy a name and call it Hooke's law. And it lets us go back and forth between stress and strain. We are assuming in every problem we solve in this class that we are always below the yield stress. We are assuming that everything is linear. We are assuming that everything is elastic. Elastic means no permanent deformation. So if you put a load on and you take it off, it will bounce right back to its original state. We also had a couple more things in this chapter. We had Hooke's law for shear, which looks like tau is equal to G gamma, where tau is your shear stress, G is a material property called shear modulus, and gamma is that good old shear strain, which is a angle change in radians. The other thing we had was something called Poisson's or Poisson's ratio. Only people who speak French call it Poisson's ratio. Everyone else calls it Poisson's ratio. It is the Greek letter nu, and it is minus the ratio of a lateral strain to a longitudinal strain. And this, I think, always needs a picture to go with it. The picture I want you to have is, here's our original shape. I am going to apply a force to it, which is going to cause it to get longer. And when it gets longer, it's also going to get a little bit smaller in diameter, because that's what tends to happen to things when they get pulled on. We call that strain in this direction your longitudinal strain. It's going to be positive if you're pulling in tension, and we call the strain in the other direction the lateral strain. So the ratio of those is called Poisson's ratio. For many materials, it is around 1/3. And how do we typically use all these material properties? Well, I think we did an example in here where we had a force of, say, 700 pounds on a bar. And from there, we could find stress. It's just force over area. Once you have stress, you could then find, using Hooke's law, strain. That would be your longitudinal strain. It's going to be stress over Young's modulus. From there, you could then go and find length change. This definition of strain is change in length divided by original length. You could also find lateral length change. It would be negative Poisson's ratio times epsilon longitudinal. And we could do something similar with shear. What we did in this chapter is we really just used the definition of normal stress, Hooke's law, definition of normal strains, to go from, if you apply 700 pounds, how much longer does it get? And then we moved into another chapter where we actually put all that together into a single equation. That single equation said length change, we started using a lowercase Greek delta for it, is the force times the length over the area times the modulus, or we would sometimes write this as the summation of all of the forces times the length over area times E. The really important thing that I want to mention here is this F must be the internal force, which is not always the same as the externally applied loads that you see. The picture for axial loading is all of your loads are basically lined up in the direction of the axis. And if it looks like this, you're going to need to take cuts in each section where the loading changes in order to find the internal force in that part of the bar. And that is the force that goes into either of these equations. Our sign convention that we used for that was that anything that is being pulled in tension is positive, and anything that is being pushed in compression is negative. And that needs to go into this equation as well. As you're summing these up, you need to add up all of your positive tensile sections and subtract any of them that are compressive so that you get the right total length change. Let's talk statically indeterminate for a minute. There are 3 different pictures you might have for statically indeterminate. One is that classic bar between 2 walls problem with a force applied to it. Another is the composite bar or cylinder type problem where I've got a material on the outside and a different material on the inside, and then we've got a load being applied. And finally, we occasionally had these problems where we had, maybe 3 different bars with another bar attached to it, and maybe depending on how the loading was applied, maybe this thing deformed not straight up and down. And so we had different length changes for our 3 different bars. Okay, in all cases, your solution process is as follows. First, draw a free body diagram. Try to relate the forces. you probably can't solve for all of the forces. In fact, that's what makes it statically indeterminate. We want to relate the forces to each other as much as we possibly can. Our second step then is to write those equilibrium equations. That's how we relate the forces to each other, is through the equilibrium equations. And finally, we need compatibility conditions. Compatibility conditions take one of three forms. For this one, first picture that I have, we're going to have something like delta 1 plus delta 2 equals 0. For the one in the middle, we might have something like delta for concrete equals delta for steel. And for this last one, if this was delta A, this was delta B, and this was delta C, we might end up with something from similar triangles, where we get delta C minus delta A over L equals delta B minus delta A over L over 2, as an example. So the nature of the compatibility equation totally depends on what style of statically indeterminate problem it is. But compatibility conditions are always relationships between the deltas. And then what you're going to use is that each of those deltas is equal to an FL over AE equation. Because remember, your equilibrium equations are all full of forces. So we need to replace all the deltas in whichever of these compatibility conditions we use with all of these, an equation that gives you force instead. And that lets you combine your equilibrium equations with your rewritten compatibility equation to solve for your unknowns. All right, thermal. Our main equation is that epsilon thermal is equal to alpha delta T, where alpha is a material property called the thermal expansion coefficient. And when we are free to expand, what happens with a bar is it just gets longer. And the amount it gets longer is our delta thermal, which is equal to thermal strain times the original length. So if there is my original length, it will just get longer. But the more interesting problem is when it is not free to expand. So for example, we have a bar between two walls, and it might be sitting there totally stress-free, but when you heat it up, it wants to get longer by a delta thermal. And so what happens is you end up with a big induced load P, which is going to cause it to contract by a delta mechanical. The equation we end up writing is the delta thermal, which is a positive amount, and then when you subtract from it the delta mechanical, which is a contracting amount, they have to end up equaling 0. And there are a few different ways you can do the sign here. I tend to draw P in the direction I think it's going to act and draw my delta thermal and mechanical the way I think they're going to act. So I would say delta thermal is going that way, then we're going to subtract from it how much it contracts to set it equal to 0. Then we just replace those with what they're equal to. The delta thermal will be alpha delta T L, and the delta mechanical will be PL over AE. That has to add up to 0, and you can solve for whatever thing you don't know in that equation. The more complicated case would be, what if we had two dissimilar materials sandwiched together like this? They want to expand different amounts. Let's say the outside material wants to expand more than the inside material. So it wants to experience a big delta thermal for the outside material all the way out there. But let's say the inside material only wants to go out this far. Delta thermal for the inside material. So they're going to meet in the middle somewhere. Probably not exactly in the middle, but they're going to meet somewhere in the middle, like right here. So to do that, the outside material is going to have to experience a big mechanical force and a delta mechanical for the outside that causes it to not go as far as it wants. Whereas the inner material is going to have to experience a delta mechanical for the inner. The way that happens is that the inner material pulls in on the outer material, and the outer material pulls out on the inner material by equal and opposite forces, because the forces have to sum to 0. So when I write this equation down, I end up writing that delta thermal for the inside material plus delta mechanical for the inside material has got to exactly equal delta thermal for the outside material minus delta mechanical for the outside material. And that becomes your compatibility condition. Each of the thermals get replaced by a alpha delta T length, alpha delta T length for the material, and each of the mechanicals get replaced by a PL over AE. And then depending on your geometry, will determine whether those P's are the same. If I were to cut this open, here's my cut open face, to see what's actually happening load-wise, what's happening is that the outer material is pulling out on the inner material with a force P. The inner material is pulling in on the outer material with a compressive force. This would be our P inner and P outer, and if you sum forces in the X direction, you'll find that P inner has to equal P outer, and that's what you would plug in over here. There's thermal really, really fast. Let's go through torsion. Our two governing equations are angle of twist is TL over JG, and shear stress is T rho over J. Things I find students have difficulty with is remembering that T is internal torque. So you do need to take little cuts to find it. Rho is the radial location where you want the stress. So if you plug in 0, you get 0 stress because there's no stress at the middle. If you want the biggest stress, put in your outer radius. And J is polar moment of inertia, and this is in radians. Nobody has too much trouble with G because I usually give you G as part of the problem statement. It is just a table lookup. It is shear modulus. The sign convention tends to give people problems sometimes. Sign convention for torsion is arrowheads outward is positive, so use your thumb to figure that out, that this would be T, that would be T, and there is your positive. Negative is opposite with your right thumb going in on each of the ends. And the last thing we typically do is figure out the direction of the shear stress. So if I have a torque going this way, I like to draw little arrows all the way around the circle to help me figure out for a particular point I might pick. Let's say I'm picking this point right up here at the top and I want to know the shear stress right there. Well, I like to draw a little box that has a roughly similar perspective so that I can tell that this face matches this face. And then I just look at which direction the little purple arrow is right there. It's going to the right. So on my diagram, I draw it to the right. And that is the most important arrow to draw on there, though you should also draw another one that is head to head, tail to tail with it. And if you feel really ambitious, you can draw the matching ones on the back and other side, but I don't require those when I'm teaching the class. I only care about the ones on the two visible sides. All right, that's it for the exam review for next week's midterm exam.